Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so it's my pleasure to introduce Hari Narayanan from the University of Washington. So many of us in the room have been working with self-concordant barriers, and Hari will tell us about how to use them for the problem of sampling.
So, thank you for the invitation to speak here. It's a pleasure to be here. So the title of my talk is Randomized Interior Point Methods for Sampling and Optimization. So in this talk, I'll put together work that appears in 3 papers. The first was joined with Ravi Kannan and was called Random Walks on Polytopes and an Affine Interior Point Method for Linear Programming. Then in later work, I generalized this to hyperbolic barriers and other self-concordant barriers. So and I also will talk about an application that is joint work with Alexander Rakhlin to regret minimization. So the task of randomly sampling a polytope has the following form. We are given a p and n-dimensional polytope given by m linear inequalities and an interior point x. The task is to sample the polytope at random, and we will discretize the diffusion process designed to mix fast. So why should one be interested in sampling polytopes? Well, one application is to sampling lattice points in polytopes. This gives rise to algorithms for sampling combinatorial structures such as contingency tables, and it also gives rise to algorithms for volume computation. That is the task of sampling a polytope is used as a black box in volume computation algorithms, and which in turn leads to algorithms for counting lattice points in polytopes. And finally, as I'll discuss today, these give rise to randomized interior point methods for convex optimization. So the model for past work has been somewhat different in this area. The convex sets are specified using what is called a membership oracle. Sorry. So the convex set is invisible, unfortunately, but it is sandwiched between the 2 balls here, the inner ball and the outer ball. And yeah, given a query point x, one receives a yes answer if x belongs to the convex set and a no otherwise. So past approaches to sample convex sets have included the grid walk due to Dyer-Fries and Kannan, which had a mixing time of n to the 23 from a warm start after preprocessing. By a warm start, I mean a starting distribution whose L infinity, so the L infinity value of the Radon-Nikodym derivative is bounded above by a universal constant with respect to the stationary measure. So this is how the grid walk works. You basically take small steps on a grid. And then another walk considered by Kannan, Loaz, and Simonovitz is called the ball walk. Here you take a ball of a certain radius around the current point, pick a random point in the ball, and repeat this procedure. And this was shown to have a much faster mixing time, that is O star n to the 3 from a warm start after preprocessing. Then there's this random walk called hit and run that was first analyzed by Loaz, and then the analysis was elaborated upon and improved by Loaz and Mempala. Here in one transition, you pick a random chord and pick a random point on that random chord and repeat this. And this was called hit and run. The mixing time from a fixed point was order n cube r by r squared log capital R by d epsilon, where d here is the distance of the initial starting point from the boundary, and r, capital R, is the radius of the circumscribed ball, little r is the radius of an inscribed ball. And epsilon is the the total variation distance to the uniformity that you desire. So the mixing time from a fixed point is an order n more than the mixing time from a warm start. And this is related to the fact that in high dimensions, if you have a single point and you take one step, then you essentially start with a distribution whose L2 norm is exponentially large in n. And so you pay a penalty of n when you're starting from a fixed point. So for a polytope with less or equal to poly n faces, capital R over little r is cannot be better than order n to the half minus delta, and this is in fact true only for symmetric polytopes. If you have asymmetric polytopes, then what you need to do is you need to put them in a certain position, and then you need to shave off their corners by intersecting them with a ball of radius root n or so. So it's not that you actually can sandwich the entire convex set between balls of radius 1 and root n. You actually have parts that stick out of the outer ball, but they are very small in measure, so you can ignore them. But this gives n to the half, and the overall bound in the mixing time from a fixed point is therefore n to the 4 minus delta. So this n cube and this n give n to the 4 minus delta. So the mixing time of the new Markov chain that I'll discuss today is as follows. It is for sufficiently large n, the mixing time from a fixed point is this quantity m is the number of faces of the polytope, n is the dimension, s is the notion of centrality of the chord, which is the maximum value of this longer part divided by the smaller part, taken over all chords passing through the point x. So
x is the starting point?
X is the starting point. Yeah, so for sufficiently large n, the mixing time is this to get to epsilon total variation distance. And from a warm start, the mixing time is order mn. So I have a somewhat crude upper bound on the number of arithmetic operations it takes for one step, which is m to the gamma. Intat has a better analysis which gives essentially number of non-zeros in the matrix of the polytope plus order n squared. So this m to the gamma can be replaced by something like that. And as a corollary, we see that the number of random walk steps to mix is smaller for this walk if the number of faces is order n squared, and has less arithmetic operations if m equal to order n to the 1.46. Again, with Intat's better analysis, this becomes order n squared as well. This m becomes order n squared as well.
Is there any condition on the polytope being isotropic?
No, so the random walk that I'm going to describe is affine invariant.
Okay.
So it won't matter.
Interesting.
So this is so in order to define the random walk, I'm going to have to define Dikin ellipsoids, because this is how the one step of the probability will be of the Markov chain will be made. So the Dikin ellipsoid of the Dikin ellipsoid of a polytope around a point x is defined as the set of all points y such that x minus y transpose multiplied by the matrix summation ai transpose divided by 1 minus ai transpose x whole squared. Here ai x less or equal to 1 is the polytope, and ai is the ith row of the matrix A. So here for x belonging to P, dx is the set of all y such that basically this vector, this deviation vector from x multiplied by, this is actually the Hessian of a certain barrier function that I'll come to, is less or equal to r squared, and for us r is 3 by 40 in the polytope case. So to take a step back, there is some convex function whose Hessian, if you take, you will get this, and this times the Hessian less or equal to r square defines the ellipsoid. These ellipsoids have nice properties. For one, if you take around any point, around the point x6, you take the symmetrization of the convex polytope, then if you take the Dikin ellipsoid and dilate it by square root m, it will contain the symmetrization of the polytope. It's too much to ask for that the Dikin ellipsoid dilated by square root m contain the polytope, because you can go very close to a corner and then the Dikin ellipsoid will be tiny. But what is almost as good for our purposes is that when you dilate it by square root m, it contains the symmetrization of the polytope about that point.
Excuse me, what do you mean by the symmetrization?
Okay, yeah, good. So it's the set of all points with the property that both the point and its reflection about the central point belong to the polytope. So it's P intersection minus P, where if it were the origin. So Dikin's affine scaling LP algorithm, this was when he proposed the Dikin ellipsoids in the first place. Do the following: you start at a point, you take a Dikin ellipsoid, and you optimize the linear function over the Dikin ellipsoid. Pick the new point. Pick a new ellipsoid around the new point, and repeat. So this algorithm has no polynomial time guarantees and is believed to not be in polynomial time. So although it's a very natural looking interior point method, it's believed not to be polynomial time. On the other hand, the Dikin walk for which I'm going to describe with some modifications leads to polynomial time algorithms for linear programming. And the Dikin walk, now that I've defined the Dikin ellipsoid, I can talk about the Dikin walk. It's defined as follows. I take a point, take the Dikin ellipsoid around that point, pick a random point inside the Dikin ellipsoid, look at the new Dikin ellipsoid. Now if the new Dikin ellipsoid contains the old point, then accept this point with a probability that is proportional to the minimum of 1 and volume of dx0, the initial Dikin ellipsoid, divided by volume of dx1, the new ellipsoid. And if the new point x0 does not belong to dx1, then don't accept the move at all, just reject the move. So this is the random walk. And as you see, it goes through, if you start at a corner, the ellipsoids are small, but as you move closer to the interior, although in high dimensions you never really go close to the interior, you kind of move along the surface of the polytope. But still, when you're far from very low dimensional corners, the sizes of these ellipsoids become bigger. So this is a natural discretization of a Brownian motion with drift on a certain manifold, where the metric is given by these ellipsoids are the unit balls in the tangent spaces of the metric. And that diffusion process obeys a certain Fokker-Planck equation that is very much akin to the heat equation, except that the stationary measure is not the uniform measure. It's the uniform measure on the polytope. Once you equip the polytope with this different measure, with this different metric, it also gets a natural measure which is whose density with respect to the uniform is proportional to the inverse of the volume of the Dikin ellipsoids. So that is mu actually, and so there's a natural process in the background here.
So this is true even with the rejection step. That if we are not doing the rejection.
No, so I'm not claiming an exact correspondence. I'm just saying that this is the morally, this is I don't know if with the rejection step you take delta tending to 0, you actually get this process or not. I don't know if formally that's true. So the hit and run of Loas involves transitions where starting at x, you draw a random chord, pick a random point on the chord, and the mixing from a warm start. I'm sorry, this slide should not be there. So the mixing time from a warm start here is mn, whereas the mixing time from a warm start here was n cubed. So this algorithm was used in mixed integer programming by Huang and Mehrotra. The idea was that you want to find not only a point with a large objective value, you want to find a point which is integral and has a large objective value. And to do this, what they did was they basically, instead of doing a normal interior point method, they used a variant of Dikin walk, short and long step Dikin walks. Then they got a point that was not exactly optimal, but kind of close to optimal and a bit random. And then they did some additional stuff to make it an integer point. They basically rounded it, and if it landed outside the convex polytope, they took the nearest point in the convex set to that new point, and then again rounded it and did this repeatedly. And in the end, they would get a current integer solution, and then they set a cutting plane at that integer solution and repeated the whole process. So that was what they did. So the way we are going to analyze the Markov chain here is by getting a lower bound in the conductance, and the conductance phi of this Markov chain is obtained by taking the infimum over all sets S of measure less or equal to half of the probability of exiting S from a random x in S1. So you pick a random point in the set and you take a random step and evaluate the probability that during this experiment you move from one side to the other side. And so Loas and Simonovitz in 93 proved the following bound. They proved that starting distribution has density rho, where the supremum of rho x is equal to m. Let x0, x1 be a random walk. Then for all values of s, the probability that xk belongs to s minus mu s is less than square root m e to the minus k phi squared by 2. And so even if m is exponentially large in n, that gets translated to an additional n factor in the k, and you can get bounds from a fixed point as well. So this tells us that the mixing time from a warm start is 1 by phi squared. And now the question is, how do we bound the conductance? So the way the conductance is bounded in this situation is you first get a lower bound which is purely geometric on the convex polytope with this different metric, and then show that the transition probabilities of the Markov chain are in some sense are faithful to this metric. So if you take 2 points that are geodesically close by, then the total variation distance of the transition kernels corresponding to those 2 points is 1 minus omega 1. So it's bounded away from 1 by omega 1. So I described you take the convex set and then you give it a metric where tiny distances are given by the ellipsoids. So the ellipsoids are circles, ellipsoids are the unit balls in that metric locally. So for that metric space, we want an isoperimetric inequality. So, and it turns out that Loas analyzed hit and run with a different isoperimetric metric called the Hilbert metric, and that this metric is approximately isometric to the Hilbert metric up to a square root m factor, and that allows us to analyze the isoperimetric constant of the Dikin metric using the isoperimetric constant of the Hilbert metric. So here is what the Hilbert metric is. If you take 2 points x and y, you define sigma of xy as x minus y divided by u minus v multiplied by u minus v divided by u minus x divided by y minus v. So this is projective. This is not yet a distance. So this is a projective ratio, and if you take log of 1 plus this, then that becomes a distance. So log of 1 plus this is a distance. And what Loas proved was that if you put any uniform measure on this polytope and you partition it into 3 parts, P is the polytope, S1 prime is this part, S2 prime is this part, and P minus S1 prime minus S2 prime is the part in between. Then the measure of P multiplied by the measure of the part in between is greater or equal to sigma, the distance between the 2 parts multiplied by mu of S1 prime multiplied by mu of S2 prime. So by distance between the 2 parts, I mean the distance between the nearest pair, x and y, x in the first part, y in the second part. So this gives rise to an isoperimetric inequality in our setting also. So here this is the metric, it's given locally it's given by a Dikin ellipsoid. So there's something not working right with my slides, but what? Okay. So
Use the whiteboard maybe.
yeah, if I need something, I'll use the whiteboard. Yeah. So as I mentioned before, the Dikin ellipsoids, if you dilate by square root m, they contain the symmetrization of the polytope. And what I forgot to mention was that they, as stated, are contained inside the polytope. So there is this the symmetrizations of the convex polytope about a point are sandwiched within square root m of the Dikin ellipsoid and its dilation. So because of that, the Hilbert metric is within 1 by square root m of the Dikin metric, and this gives rise to this isoperimetric inequality for the Dikin metric. If you have product polytopes, then you can do better, because if you take Riemannian manifolds which are products of smaller Riemannian manifolds in dimension, then the worst isoperimetric cut is not much worse than the worst factor. And so this m can be replaced by the m of the smaller polytope, which are used in the direct product. But that's a special case. So next, the second step is to be able to relate the total variation distance between the density functions, the transition density functions for 2 nearby points. For this, so here I want to make a point that actually I said that everything is a Dikin ellipsoid and so on, but once you do the rejection step, that rejection step is very extreme in the case of polytopes, because we are taking pretty large steps and you end up actually rejecting one whole side of the polytope in the worst case. So they don't really look like ellipsoids anymore. They look like these sort of things, and you need to argue about the overlap about these sort of things. So the lemma is that if the distance is less than 1 by root n, then nonetheless the total variation distance between px and py is less than 1 minus omega 1. And how does that go? So basically we are going to use the isoperimetric inequality, and what you say is that let's consider one particular. We wanted to say that I'm sorry. So that discussion here. This is a lemma which I'll discuss a little later, perhaps. But I'm going to talk about the consequence of this lemma to conductance. So we want to bound the conductance, and we want to do so using the isoperimetric inequality. So what we do is we take a cut, And then we say we want to find out what's the probability of moving from S1 to S2, and we want to give a lower bound on that. So we associate with S1 prime, which is a set of all points in S1 such that Px of S2 is less than delta by 2. So these are somehow deeper inside S1 prime, these points are deeper inside S1, and they don't actually go into S2 with good probability. And similarly, we associate with S2 and S2 prime, which are points deeper inside S2, which don't go into S1 with good probability. But what we want to say is that the mass of the intermediate portion that is in between this is actually large, and that portion corresponds to points that are going to the other side with good probability. And so the probability of going to the other side is large. So that's going to be the argument. So let x belong to S1 prime, y belonging to S2 prime. Then this implies that the distance of Px and Py is greater than 1 minus delta, because Px is mostly supported inside S1, and Py is mostly supported inside S2. And because these things are so far apart, by the lemma, the x and y must have been far apart, because we know that if x and y are close by, then dpx, dpy is also small. So x and y is far apart. But now we are in a position to use the isoperimetric inequality and by the bound in the Cheeger constant, this measure of this part in between is large, and it has measure omega 1 by root mn. The 1 by root n comes from here, and the 1 by root m comes from the original isoperimetric inequality for the Dikin metric. So therefore the points in the band jumps to the other side with probability omega 1 implies that phi is greater or equal to 1 by root mn. So this is the argument that the conductance is omega 1 by root mn. So to prove the lemma, we have to, I'm not going to prove the full lemma, but let me just tell you what are the steps. So certainly if you want to prove that if 2 points are close, then dpx, dpy is bounded away from 1, you need to be able to show if 2 points are infinitesimally small distance from each other, then dpx, py is bounded away from 1. So that is related to the probability of a proper move. So the probability that you're not stuck at a given point. So suppose you want to show that you're not stuck at a given point with good probability, what you need to show is that first of all, when you make a move from x to, when you pick a proposed point, then the x point is likely to be contained in dx, d omega. Because if this is not likely to be contained in d omega, then we are dropping it with 100% probability.
So sigma, what distance is this one?
So sigma, here I am using the Loa's distance. So this lemma is not in terms of the Dikin metric, it's in terms of the Loa's metric, but the scaling is right. So this rho x y is going to be 1 by root n in this case.
I have forgotten what d omega is.
You have forgotten what?
What was d omega?
D omega, this is the Dikin ellipsoid centered at omega.
Oh, okay.
And omega
What
is
is
W?
Yeah, W, sorry. DW.
Oh.
Yeah, x is likely to be contained in dw. So this is something you need to show, because otherwise every time you make a move, it's going to be impossible to come back, and so you'll be forced to reject it. When you impose a metropolis filter, you need to impose it in such a way that the moves that go in one direction are also moves that can go the other way. Otherwise, it's not going to be reversible, and we don't know how to analyze non-reversible Markov chains in this setting. So the volume of the new ellipsoid is unlikely to be much larger than the current one, because if you recall, there were two things that involved the rejection. The first was whether it's there in the old, if the new point is contained inside, if the new Dikin ellipsoid contains the old point. And the second was the ratio between the volumes of the two Dikin ellipsoids. So we don't want the volume of the new ellipsoid to be much larger than the current one. So we prove something like this. So
what is FC?
It's the error function.
Error function. So the step 2 follows from these two steps. First is that the gradient of the log of the volume of the Dikin ellipsoid, this is also known as the volumetric barrier, is less or equal to square root n in the local metric. So if you take a Dikin ellipsoid, rescale so that Dikin ellipsoid is the unit ball, and then you measure the gradient of the log of the volume of the Dikin ellipsoids around it, then that is less or equal to 2 root n. And we know that when you pick a random point in high dimensions, the dot product is going to be like 1 by root n. So that 1 by root n and this 1 by root n cancel, and you get the bound that we want. So that is of course the linearization, but Nesterov and Emirovsky have shown that the log of the volume of dx is a barrier, in fact, which means that it's convex. So log of this should be negative log of, so this is a concave function. Its negation is a convex function, which completes the proof because of this inequality. So that gives you a flavor of what kind of arguments go into proving that the total variation distance between the transition probabilities of nearby points is going to be small. So the final result is that if you let tau be greater than some number, then if you let x0, x1 be a Dikin walk, then for any measurable s in P, the probability that x tau belongs to S minus mu s is less than epsilon, and S measures centrality of x0 in Q. So now that was the first part, was based on work with Ravi, Kannan. Now I'll talk a little bit about how to extend it to arbitrary convex sets. So this is going to be using the concept of a self-concordant barrier. So a self-concordant barrier is a function from P to R. It is convex as x tends to the boundary of P, f of x tends to infinity. For any vector h, point x in P, the following hold. The gradient of f of x in the direction of h, so the derivative of f inner product with the vector h is less or equal to square root nu times the norm of h. And the third derivative of f in the direction of h is smaller than the Hessian raised to 3 by 2. Hessian matrix, entry of the Hessian matrix raised to 3 by 2.
Okay, yeah, there are a bunch of things here that we like here. For example, what is nu?
So nu is the barrier parameter, yeah.
Parameter, okay.
Barrier parameter.
Quantify for all for any vector h. And for all x, right?
Yes, for all x, for all h. Yes.
And the last thing.
The last thing is the smoothness of the Hessian.
Is 3/2
Yes, that's
constant
right.
which has a
You
meaning
have
here?
to, because this is a third degree form and this is a second degree form.
Yes. Okay, yeah, sure. Sorry, that was not a big question. Okay.
So if instead, in the last inequality, if on the right-hand side, instead of the Hessian, you put the identity, then you're saying that the third order derivative is just Lipschitz. I mean, it's bounded. So you're saying that the second derivative is Lipschitz. And now you're saying the second derivative is Lipschitz with respect to itself.
Okay. I kind of remember you saying this. These same words before? Okay, yeah.
Slowly seep in.
Okay. It's kind of making sense.
So a hyperbolic barrier is a very special kind of barrier which comes from being the logarithm of a polynomial, and it's a polynomial that has only real roots in a certain fixed direction. So what you do is it's a multivariate polynomial. You fix the x and you take a vector v and you look at p of x plus tv. This is now a univariate polynomial for a fixed x, but it has only real roots. So this is called the hyperbolic polynomial. And the when you take the negative log of a hyperbolic polynomial, you get a hyperbolic barrier. And the hyperbolicity cone of P is defined as basically the set of all t. So you fix the x, and then for all values of t greater or equal to 0, so you fix a v, and now you look at all those x's such that if you take a ray in the v direction, you never encounter any real root. So that's the hyperbolicity cone. And minus log b is a hyperbolic barrier for CPV or any affine section of it. This is important because it means that you can intersect the cone with a linear subspace, and it gives you a large class of convex sets which you can express as sections of these cones.
That's always true. It doesn't have to be the hyperbolic barrier.
Yeah, sure. But you get a barrier for those. So what I didn't say was that you get a barrier for those convex sets as well by virtue of this. Yeah. So the log det of a convex set defined by semi-definite constraints arises from P equal to det x, and here x is a cone of positive semi-definite matrices. So this is used a lot, so we considered the intersection of a polytope with the supports of a hyperbolic and a self-concordant barrier.
So maybe just so that people get an intuition, another example than the same example, but just if you take the product of xi's, then you get the positive alternate.
Right. Very good. Yeah. So if you take the one hyperbolic polynomial is x1, x2 up till xn. And the hyperbolicity cone of this is the orthant. So the LP, the log barrier that I spoke about is actually also a hyperbolic barrier. It defines the orthant. Yeah, thank you. So what we do in this case is, if you have an intersection of a polytope with supports of hyperbolic and self-concordant barriers, we construct a new barrier by adding weighted sums of the previous barrier. So FL is the original logarithmic barrier, n times FH is the hyperbolic barrier, n squared times FS is the self-concordant barrier. So I need to wait. Yeah.
So no, lost me. What is FL again?
FL is the log barrier for the polytope, because there's a polytope
setting.
No, so I'm now looking at a convex set that is the intersection of a polytope, a convex set coming from, say, an SDP, and some general convex set that has a self-concordant barrier around it. So this is the most general setup you can look at. I could have said just let it be an SDP, let it be a self-concordant barrier corresponding with a convex set. But then my bounds are not as good for a self-concordant barrier. So I want to show that in this setting I get reasonable bounds. So that's why the scaling factor is what makes the bounds worse for self-concordant barriers and for hyperbolic barriers. The mixing time for the Dikin work from Wormstad is order mn plus n squared mu h. So this is the constant of the self-concordant barrier of the hyperbolic barrier, and this is the constant of the self-concordant barrier. So this is the thing. You recover the results for polytopes up to constants by when you set these to 0. So this is the general setup. So now I'll move on to linear programming. Were there any questions regarding that?
Yeah, again, so on the previous slide, so Fs is a general.
Yes.
Okay.
So it's some convex body and for which you have a self-concordant barrier, is it?
Yes.
And what property of hyperbolic barriers do you use to remove the factor n?
The fact that you can take fourth derivatives.
So it could be that the entropic barrier verifies this also in general.
I see.
For any context. But
I see.
I think it's true actually.
I see. So that would give good bounds.
Yeah, but then it's not computable.
Something with sampling, right? But I guess there's a bootstrapping problem.
Yes,
Okay.
that's right.
Yeah, so now I'll move on to linear programming. So here the model for linear programming is you have a polytope bx less or equal to 1 and you want to find argmax y belongs to q c transpose y. Okay, so this is what Karmarkar's algorithm basically does. You write the polytope as the intersection of a simplex with a affine subspace containing the origin, and then you take the ball and you make a move within the ball intersected with the affine subspace in the direction of the objective. So you get a new point. And so now here is the special thing that you do. You do a projective transformation that maps the old point back onto the origin, and of course the whole subspace also changes in this process, but it's still a linear subspace. The projective transformation preserves the boundary of the simplex, not pointwise, but as a set it preserves it. And now you do the same thing. You repeat and so on. So this is actually a slight simplification of the algorithm, but this is the key idea of projective transformations that he uses. The Dikin algorithm that I described has a similar way of looking at it. Here you do affine transformation. So you write the polytope as the intersection of an affine subspace with an orthon, and then you do a optimization over the ball on the subspace, and then you do an affine transformation to move it back to the center, and then you repeat. So in Karmarkar's, the view from the polytope might be something like this. So interestingly, the ellipsoids there are not centered. So they are projectively invariant in the sense that if I took this picture, took a point, and took the ellipsoid and did a projective transformation of the whole picture, then the corresponding Karmarkar ellipsoids would be the projective images of these things, whereas that is not true for the Dikin ellipsoids. So you do something like this. Whereas for Dikin, the view of Dikin, the ellipsoids are invariant, affine invariant and centered. So you keep moving like this. So we'll consider the following approximate formulation of linear programming, which is equivalent to the standard formulation. So given Q such that y of given a polytope given by this form of inequalities, if there is a y such that C transpose y is greater or equal to 1, find a y in Q such that C transpose y is greater or equal to 1 minus epsilon. Okay, so this is the kind of program we are interested in. And the algorithm involves doing a random walk without the ratios of volumes in the metropolis filter. You still require to reject all samples that correspond to moves that you cannot reverse, but you don't need to add that other metropolis filter for the ratio of the volumes. So you do this random walk. It suffices to take a small number of walks. The first move is, however, this is very important. You have to do a projective transformation. So this is very much like Karmarkar's algorithm, except that we do it once, and we don't. And when you do this to a polytope, it really blows up. So the parts near the top where this thing u is going to infinity, and it kind of over here it looks like it's very easy to optimize such a polytope because you know the direction, but actually it's going to be a high dimensional polytope, and there will be some direction in which it is unbounded, but you don't know that direction, and detecting that direction from the faces is very difficult. So which is why you need to do something iterative. So here you map that to infinity. So we have a special subspace that is a slightly translated version of it that gets mapped here, and we basically choose a random point inside this polytope. And this what happens is that this tiny band here, which looks very tiny here, is actually huge over here. So if you start here and you do a small number of random walk steps, you end up here with high probability. And the analysis again involves the cross ratio, because as a projective transformation, the cross ratio is preserved. so you can do the analysis neatly. So this is so we do a modified Dikin walk for a prescribed number of steps, and output this, and you get a good point in the end. So this is how the walk might look. I didn't draw any rejection steps, but it basically goes up faster and faster. So now I'll quickly go through one application which is joint work with Sasha Rakhlin. So this is to online convex optimization. Here the model is that nature chooses bounded loss functions f1, f2, and each time t, an agent chooses x. An agent has to choose a xt belonging to k, and nature reveals ft, and agent suffers a loss of ft of xt. The agent's goal is to minimize the regret, which is the total loss that he incurred. This note that nature reveals ft after the agent chooses xt. So this is the total loss incurred by the agent minus the optimal loss that any fixed play of x would have incurred with hindsight. So this is infimum over all x in k. So you're comparing the best possible strategy with the best fixed move x, which has knowledge of all the ft's. And so here is the scheme. Yeah.
So you compare your strategy to the best possible fixed point, not the best possible strategy, right?
Best, yeah, fixed point. Yeah, that is it's a very trivial strategy, but yeah, yes. The best fixed strategy is fixed point. Yeah, best fixed point. Yeah. So the scheme is as follows. At times t equal to 1 to t, you sample xt from mu t whose density is e to the minus st of x, where st of x is eta summation ft of x. So this is an exponential distribution restricted to the convex set, and there's a learning rate of eta that is 1 by root t. So the thing is, if you sample from this, it turns out that it's good enough. But the question is, can you sample from such a moving distribution? Because the FTs are now changing, and you want to sample from it efficiently. And it turns out that the Dikin walk can do that, with the appropriate metropolis filter. But you need to change the filter at every time based on the knowledge of FT.
Maybe just another comment, which is, so on the previous slide, if the LT could be convex function, right?
No, actually I'm looking at linear functions. Yeah.
But there could be convex functions, and then it's enough to just look at the linearization.
Oh, I see. Okay.
In the previous algorithm, and everything works.
I see. Yeah, so this is the theorem that we have. These are linear functions with Lipschitz 1, and then the appropriately defined time homogeneous Dikin walk provide a sequence x1, x2, x2, x3, etc. that does well. It's a good strategy in this sense.
Sorry, so you're taking just one step at a time, or what? No.
Yeah, one step at a time.
That goes to the next.
So what happens is, at time t, it is very close to a stationary distribution depending on t. At time t plus 1, it's very close to a stationary distribution depending on t plus 1. So it moves basically. You have to learn the distribution, and it moves with the. So the random walk mixes fast enough that it can track a moving distribution. I think that's the best way to say.
So, but xt and xt plus 1 are just one step after the other, or do you take a bunch of steps and
one step after the other?
One step after the other, but still it makes the first. Okay. What's the linear function solution?
Okay. So thank you.
Questions? So is the proof completely different for the last thing you showed us? When you have to track a moving distribution?
No, so in L2, if you can get good enough bounds, then I think those Bregman divergences that are involved you can bound those also. So the key is to get L2 bounds on the distribution with respect to the stationary distribution. So it's the same. They're all conductance based.
Is there some dependence on the mixing time on m is necessary?
On the constant, yes. So I didn't tell you what the dependence. I just said orders t square root t. So there's some polynomial dependence on s.
No, I meant is the dependence on the number of facets of this polytope necessary?
So
it's a little odd because you said that, okay, so in the membership oracle world where you just want like a well-rounded set, somehow like polytopes with few facets are the worst, right? Because you can't have, I mean, balls are the best.
They're worst in the sense of sandwiching.
Of sandwiching, yeah. But for you, it's kind of the opposite. Like so for you, if you just look at the bounds, if you take like a polytope with a lot of facets, which is very close to a sphere, and so it can be sandwiched very nicely.
Yeah.
But from your analysis, at least.
No, I think that's a problem with Dikin Ellipsoid, right? I just write the same constraint to you 100 times. Your Dikin Ellipsoid will
basically, right? So it will be tiny.
Just string will become tiny. It's basically.
So using the Dikin Ellipsoid is what makes this.
Yeah, so it
makes sense.
I guess so. Like I don't know. My question was supposed to be like, do any other natural ellipsoids make sense? Maybe I take the max volume ellipsoid contain your body at that point.
Yeah. So I had got a polynomial bound using that. It was not a very good polynomial bound, but yeah. So the max volume, John's ellipsoids give that bound. Yeah.
Because like the ellipsoid intuitively one should choose them depending on the body, not depending on the representation.
Yeah, but the thing is, these things are extremely smoothly varying, right? So there's a trade-off. So John's ellipsoids don't vary that smoothly, and so you lose out in the bound of total variation distance because the shape changes very rapidly when you move the point a little bit. That analysis.
But you could use a universal barrier. I mean, then there is a computational cost. But in terms of varying smoothly, you can vary smoothly and just depend.
That's true. So that n, but I told you there's an n squared for mu s for me. So that n squared is because I don't have control over the volumetric barrier of a universal barrier.
I see.
So that is one reason, and other
is the canonical barrier. The volumetric barrier of the canonical barrier is the canonical barrier.
Oh, I see. Yeah, so that's
sorry, we can repeat that again.
So you know there are three universal barriers. One of them is the canonical barrier, and the canonical barrier has the property that if you take the volumetric barrier out of this, it doesn't change. It's a fixed point of this operation. But it's also impossible to compute.
Yeah.
All right. Thanks.
Thank you.